All quantum computing in 20 minutes. To start with this, we first need to understand classical computing. And it is just two states, 0 or 1. The light will be on or off, and this is what binary is. Everything that you type from alphabets to numbers, everything that you text your friend is just a long sequence of binary. The fun emojis that we love to use are again sequences of ones and zeros. And so are the audios, videos, code, Instagram reels that we share with each other. The computer understands it as binary. But how does it understand? Using transistors. Transistors are tiny switches that control the flow of electrons. When there's a barrier, the flow does not happen and we're in state 0. And when the transistors remove the barrier, the electricity easily flows and we're in state 1. And this control of switching on and off is what entire classical computing depends on. How small are these transistors? Imagine just a small coin in your pocket. It has billions of transistors inside it. Well, not inside the coin, but if there's a microchip of the same size, it would have billions of transistors. And we observe, and we call our observation Moore's law, that in every 2 years, the number of transistors in the same microchips doubles. That's a lot. That's exponential growth. And because of this, today, the size of transistors is pretty comparable to that of an individual atom. If atom is the size of a man, in this case Spider-Man, then your transistor is the size of a building. And when this happens, something weird happens. Our analogy doesn't work anymore. Our tap starts to leak, and that's quantum tunneling. Well, in classical physics, the barrier is what stops the flow of electrons. But as the size of the barrier gets smaller and smaller, and it's comparable to the size of an atom, instead of stopping the flow crosses the barrier. And because of that, the barrier is useless, and the basic building block of classical computing is shaken. So, classically, if you hit a wall, you hit a wall. But quantumly speaking, maybe sometimes you can pass through. And that's quantum tunneling. Because of this, everything messes up. This is a limitation of classical computing. After some time, our transistors will not become smaller, and because of this, our phones will not become cheaper and faster. And it'll be just as it is today, or maybe 10 years down the line. But quantum computing offers us to use these quantum phenomena to our advantage. We exploit them. And let's see how and what exactly. We'll cover the three main principles that makes quantum computing work. First, if classically we had a bit of 1 or 0 and we can be only in either of the state at a time, then in quantum computing we have qubits and they are 1 and 0 and everything in between. It's like dimming the brightness of a light instead of switching it on and off. Or you can imagine coins. If classically the coin is either head or tail, then quantumly speaking, it's a spinning coin. And while it's spinning, it's in superposition of all the states it can be. All the multiple values are stored simultaneously. It's heads, it's tails, it's one-third tails, it's everything until we measure it. And by measuring, we mean stop. And this is what gives us quantum speed up. Imagine that you send one child to search for an object in a big room. They'll look in each and every place one by one, and that's how long it'll take. But if you send many children, they'll all look at all the places at the same time and will get the answer quickly. That's superposition. If classical bits can store only one permutation in two bits like 0 and 1, then qubits can store all the permutations at once. And when we measure, we get the most probable answer instead of the right one. So we simply measure many times, and that through law of large numbers gives us the most probable answer. And because in 2 qubits, here we're able to store 4 states instead of just one, this increases the possibilities that we can check out with those many number of qubits. So if we have 3 qubits, they can actually store classical information worth of 8 bits. That's 2 to the power n. And with just 300 qubits, we can store such a phenomenally huge number, which is comparable to the size of universe. So qubits can cover more possibilities at the same time compared to classical bits. But we can't use this everywhere to our advantage. There are only certain problems which we can solve using quantum. And we know that this sort of just boils down to a linear combination. While the coin is tossing, it could be 80% heads, 30%, 20% tails. Then it's just probability. When the coin stops, it's either of the two, which is head or tail, or 0 or 1. Here, 1 for 0 means 100% probability of being in state 0. Here, 1 means probability of being in state 1 is 100%. And we can combine these two in linear algebra and represent any state, like this. So if it's 1/3 0, we'll have 1/3 here, and 2/3 of 1, we'll have 2/3 here. And we can have any numbers over here till the time there's sum square sum is equal to 1. And there you go. We can use linear combination to represent as many states as we want. And when we measure, that superposition just boils down into 0 or 1 instead of something in between. And this is sort of a bridge between quantum and classical. Finally, when we measure our systems, current systems, devices, computers, phones do understand 0 and 1, and they'll be able to understand the result. So quantum is sort of an extension to classical, not a completely different way of quantum computer, personal laptop sitting in your hands down the ages. Next is entanglement, and it's really cool. It sort of correlates 2 qubits together, and they could be positively or negatively correlated. But once you measure just one of the qubits, without even measuring the other one still being in superposition, we can know what will the measurement result be if we choose to measure. But how can that be? Like imagine 2 siblings and they are entangled. And we know now they go to a restaurant, then the girl will order a coffee. If she orders a cold coffee, then without even asking the brother, we know he'll have black coffee. This is negatively entangled, whereas if one chooses A, the other chooses B. And positively entangled would be both choose the same. But just because one of them chooses, we know something about the other one without even measuring. Sort of it's predetermined, and that's super cool. If one of them likes to do yoga, the other one will love to do gym. And if one of them likes cheesecake, the other one likes chocolate cake. At this time, I would suggest take a break and eat something. And the third principle, we'll understand with the thought experiment. So, what happens when we pass a normal ball through a slit? We expect it to be just behind the slit on the screen. That's your macroscopic particle. That's what we expect, right? Case A. But when we do the same experiment with microscopic particles like electron, A or B, astonishingly, we get B as the result. And here's how it looks. If many electrons pass through the double slit one by one, at first the pattern looks random, but suddenly we're able to see a pattern. And the pattern matches that of a wave. This would be the same pattern if you make in water. When two of these ripples interact, at certain places there is destructive interference. Both the ripples cancel each other out, and in other places they amplify and add to each other. And that's the kind of bands we get. So our electrons waves, and this property is called interference. And this sort of helps quantum computers to amplify the correct answers and cancel out the wrong ones, which we'll see soon. But yes, electrons or any other microscopic particles exhibit wave nature. And this is called wave particle duality. And just look at this image. It's so clear, so beautifully clear that this drop is a particle, but its effect is that of a wave. This really boils it down for me when I look at it. And why not? It shows us both particle and wave nature together. With these three principles of how objects behave at a small scale, we get quantum mechanics. And applying this together in real world, we get quantum computing. And quantum computing mathematically is nothing new. It's just linear algebra plus probability. So we have hundreds of years of experience in these sets of mathematics. It's really easy to implement quantum computing in those terms. So why quantum computing now? So far, what we've covered, we get that it gives us quantum speed up. It sort of amplifies the right answers. And we can entangle qubits together where we don't need to measure one and know the result anyways. That's cool. But what is a qubit physically? Definitely, it's a two-level system because to communicate with classical computing, it needs to be 0 or 1. It can't be 0, 1, and 2. So we need a two-level system. That could be your electron spin up or spin down. That could be an electron moving from ground state, getting photon or energy, moving to an excited state. So it moved from ground state 0 to excited state 1. Or lose energy or photon and move from excited state 1 to ground state 0. This also gives us a two-level system. And what else? Polarization of light. Here, when we rotate the glass, at one point, it's all transparent and we can see through. Then the translucency increases and ultimately it's opaque and we cannot see at all. That is also one way of representing qubits. Later, we'll see based on how we can represent qubits, there are many different kinds of hardwares. But this brings us back again to linear combination of 0 and 1, which is simple math that we know, and it's superposition. So either our state is like 50% 0, 50% 1, that is called uniform superposition, but it could be anything. 30% 0, 70% 1 while in superposition. But that just means that when we measure, the chances of we getting one state is 70. That's a probability. And this is a way of representing all our qubit states. The circumference, the sphere of this surface of this sphere, and all the points on that surface is actually all the possible qubits we can have, assuming that the radius is 1 unit. So how did we get this sphere? And it's called Bloch sphere, by the way. So there was this experiment, Stern-Gerlach experiment, where assume electrons were passed through a magnetic setup along the z-axis. We saw that we get two distinct places on our detector. One is spin up and other is spin down of the electron. And this just gives us the 0 and 1 state. If we repeat this along x and y directions, we get the other states. And ultimately, this Bloch sphere. So this sphere sort of represents all our qubit states. And how do we translate from one state to the other? Well, if these are vectors and we multiply them with matrices, we'll get new vectors. So just like that, we apply matrices to these. And matrices are called gates. We'll come back to that soon, but one interesting thing that this proves is Heisenberg's uncertainty principle. So just imagine you're driving a car. When you're driving a car, at every given point, you know exactly where your car was and at what speed it was moving, right? But Heisenberg says that at microscopic level, either we'll know speed or we'll know where we are. That's so confusing. If we know where we are, how can we not know what speed we're at? But that can be explained through this experiment too. If we first measure whatever wave function we have in the z direction, and let's say it measures for color, blue or green, and we get blue, and then we only pass the blue result to the next axis. Here, we measure the shape. Let's say we get a circle shape. But as soon as we get to know something more about our measurement, that its shape is circle, we forget about the color. And when we pass the state again and detect for color, we should actually get only blue, right? Because we know from before. No, we've forgotten that. And suddenly we get both blue and green. Just see, here green was not passed. Here it was not passed. Then how come green came back? This is because nature fundamentally allows us to know just as much, not everything. So as soon as we know something more, we forget about the other one. That's the same for speed and distance or position in terms of Heisenberg uncertainty principle. So now, gates. If these are our initial states or inputs, which are vectors, we can apply different gates on them, which will sort of change the vectors on the blocks here to some other position. And we'll have new qubits, new superimposed qubits in a different state. And once we measure it, we get our output. So let's see. If this is state 0, where 1 here means 100% probability of being in 0, and we use Qiskit, one of the libraries in Python, to implement this. We apply no gate. These are just barriers in the diagram. We take a qubit and we just measure it. And we apply no gate. So Qiskit by default initializes a qubit to 0 state. So once we measure our qubit, which is 0 state, should be 100% 0. And that's what we get upon measurement. The probability of being in state 0 is 1. And then there's this X gate, which is the quantum bit flip. It gives us 1 when applied to 0. It's pretty clear. This is the matrix of X gate. When applied to 0, gives us the vector of 1. It's sort of a quantum bit flip. And it looks like this. One X gate is applied. And from the probability, you can see on measurement, we get 1 100% times. Similarly, we have other gates, but this is how X gate looks on the block sphere. And this visualization just helps me understand it so much better because I can see how it's moving from 0 to 1 and all the other points that it touched while going there. Other gates are Z gate and H gate. H gate creates superposition and Z gate changes phase. And looking at this animation would make it pretty clear. So Z gate is bringing us from 0 state of the Z axis to plus state of the X axis. And then when we're in this plane, it's moving in this direction, X to Y. That's change of phase. And similarly, we have Y gate. And this, you can imagine a stick over here, which is rotating. And because it's rotating, a tangent to it, which is perpendicular, is moving like this. Now, there are some universal qubits using which we can create all the qubit gates. Just like in classical computing, we have Boolean algebra where NAND gate, NOR gate can make all the OR and AND gates. Similarly, here, H gate we just saw, which changes bases or creates superposition. C naught we haven't seen yet, but it creates entanglement. And a T gate. Using all of these, we can get any rotation on the block sphere. But what's a T gate? If this was the Z gate, which takes a full 180 degree on the block sphere, then this is an S gate, which just takes a 45 degree round. And T is even half of that. Sorry, this is 45 and S is 90. And that's it. If we apply T 2 times, we get S. If we apply T 4 times and S 2 times, we get Z. And you can already see how using T gate, we got Z gate. And through other relations, we get X gate, Y gate, and H and C naught are already universal, so we cover all options. And this is, again, an example of a circuit where this is the circuit width, means how many qubits you can use, and this is the circuit depth, means what is the longest sequence of gates applied to any of the qubits. And these parameters are more important than the qubit count. You will hear that, okay, IBM has reached these many qubits, Google has reached these many qubits. But qubits alone don't tell the whole story. The circuit width, that's the total qubits, is good, but circuit depth tells us that how many gates can we apply before those qubits start to lose their quantum properties and the answers we get are not correct but noisy. And of course, this is the important criteria, right? If we have many qubits, but we know that the answer is not right, it's like hundreds of cheap phones, whereas you can use 10 really powerful ones. So, circuit depth tells us about the quality of our answers. And then quantum volume is sort of what I just explained, how circuit width and depth both tell us how well the quantum computer works with the given number of qubits. And entanglement. We looked at the CNOT gate, and this gate you will see is different from H and T. H and T are boxes along only one qubit, but this gate connects two qubits. That's why it's a two qubit gate or a multiple gate. And we need this. Why? Because entanglement is interaction of two qubits, right? So this puts them into that interaction. And then another criteria to know about the quality of our results is fidelity. State fidelity is how close our answer is to the actual answer, and gate fidelity is how well our operations work. Higher the value, the better. Here, the two states are same, so their value is pretty close. But here they are different, so they're far away. Higher fidelity means better results. And then one more criteria. These are two times before which our gates should perform all our operations. If our gate runs longer than these times, then most likely the answers that we're getting are garbage. So, what is relaxation time? It's the amount of time that it takes for our state to decay energy to move from state 1 to state 0. Like we saw ground state and excited state, right? Once an electron is an excited state, it will not stay there forever. It will lose the energy. And when it loses the energy and goes to the ground state or zero state, it sort of lost its property, right? We started the circuit assuming that it's in state 1, but by the end of it, when our last gate was applied, the qubit was actually in state 0. And then we get the wrong answer. And decoherence time is when we're still in the state 1, but we've lost our phase. That phase that Z axis gate was doing, we've lost it. And when we lose it, it's sort of like we've lost some quantum property and answers are wrong. So the gate time, that the maximum circuit depth is the qubit which has the maximum number of gates applied on it. All those gates should run in time which is less than that of relaxation time or decoherence time. Otherwise, if that time of applying gates is more, answer is possibly going to be wrong.